So we talked a little bit about the internal implementation of pandas, and we're going to continue um, improving our code, right? So let's try to, perhaps profile the code again. So we can try something like Python 3. Let's see if we can run this line again and see how our function, see where the bottlenecks are right now. So we actually ran until, okay, let's run the statistics file, so Python 3.8 temp.py, and these are the cumulative time. So again, we can ignore this first functions that don't do much. We're calling, so out of the 70 seconds, we're spending a significant amount of time inside of this get item call, as well as compute meta information. The rest of these function calls apparently do not take that much time, but we can look for more places to optimize. For example, if we increase the cumulative number that we see on like other function calls, and where the problems add up in terms of the cumulative time. Right. Okay. We can also see things like, for instance, we're still spending 22 seconds inside here, and then we can go and look at. Let's say we try to profile this function. So let's say we profile this function now. So that would be profile m. And we want to see where the bottleneck is. And I think previously we already showed that most of the time was spent inside this function, about 80% of the time, right? So if you go back to the line there, about 80% of the time is taken inside this line, and now this came down to 18%, and we're spending about 75% of the time here, which means if you can, again, if we can apply this, so let me just do that apply raw. Okay, now we wrote that down, and right now this is our implementation. So we want to see, okay, how we can improve this. So we just constantly improving our code, then asking the profiler, okay, where is our next most problematic function, and then we're just going down the line. So this post compute is actually inside our alpha specific file. So we're no longer working with utils function, right? So we can just comment this out because we no longer want to profile this, and then we can go to our alpha1 file and then do some profiling of the post compute. Then we can also do let's say we want to profile two functions at a time. So let's say we want to do, instead of profiling compute meta info, we want to profile both the run simulation file and the post compute inside the alpha1 file. So let's see how that goes. Okay, so we arrive at the line, and let's just go over here. So for the entire run simulation file, we're spending about 25% time inside the compute meta info. So about 25% of the time is spent inside this function, of which about 70% or 80% of the time is spent on the post compute, of which about 100% of the time is spent on this line. So you can basically do the math, and if you fix basically this function, this post compute, the entire thing is just this line. It's taking up the whole time on the CPU, which means that about 80% of 25% is spent on if we can reduce the time spent by this line, then we can bring this 25% significantly down to like maybe 5-6%, right? And then the next most timely problem is about 15%, and then this line. So if you consider the function calls, okay, and then this line. So actually, these kind of statements are supposedly quite innocent, but apparently it is still taking quite a bit of time. But what should be the main focus is, okay, like about half the time is spent on these two lines, and then followed by this kind of accessing of the and then this kind of very trivial accessing logic. So this should give us a hint as to how we should improve our code in the future. So the first problem is really that we're making a lot of function calls to functions that are not implemented or they're not efficient, right? So even though, okay, this is very trivial logic, what if we can build up this logic without making a function call to add, and then only adding it at the end of the whole simulation? Then we'll still obtain the same data frame without having to make these function calls inside a for loop, which is probably what is the most problematic thing. Because if you see, if it's outside the for loop, then we won't spend that much time inside. The really problematic thing is that if it's inside a for loop, if it's inside a double for loop, and we're making function calls to data frame .add, then we're going to take up a significant amount of time. So there's not much for us to do now. The only thing we can do is basically to reduce the number of function calls, and that is going to be the focus of our next improvement. Okay, so at this point is where I want to bring in the concept known as vectorization. Okay, so let's just go over to the notepad. So we want to reduce the number of function calls. Just reduce number of function calls. So before we talk about how to do this, let us first consider what happens inside the computer, right? So inside the computer, this is going to be a very rough approximation of what actually happens inside the computer architecture, but an approximation or a rough idea is good enough. So suppose you have your disk, right? So this will be a disk. This will be a disk. You can store some files. You can store your CSV files and whatnot in all your videos. Okay, but this is quite large. And then there's a small space and what you know as a random access memory. So this is the computer, and then this random access memory, and then there is this, and then here is the CPU. The CPU basically does things like CPU does something like so this is the stuff that does like x times y plus c, and then it'll give you the answer, stuff like that. So this is the mathematical components of your computer and does all the operations. And your CPU has what is known as a L1 or L2 cache. So in order for the CPU, for example, if you want to do x times y, then you need this x and y to be inside the CPU cache registers for you to do the computation, right? If your data is all the way inside the disk, then the computing units basically cannot perform the mathematical operation. So most computing architectures basically have like hierarchical data as a hierarchical format. So the operating system, if the CPU needs some data, then it will ask the RAM, and if it's inside the RAM, then we can immediately retrieve it to the L1, L2 cache, and then we can perform the math. Otherwise, we need to ask it from the disk. And of course, there is a data bus. So this is like, basically just a bus that transfers data, and you can imagine there is a data bus to the CPU also. So how fast the data transfer? So this is said to be a data bus, right? And then there are many different properties of the bus. So for example, bus width, and then things like bus frequency. And the CPU has interesting properties such as the clock speed, and then the number of instructions per cycle, and then also things like what kind of the computer, what kind of instruction set it is running, right? So you might be running a specialized instruction set that allows you to do some idiosyncratic addition and multiplication at the same time, or something along those lines. So the crux of what we want to emphasize is that in order for us to do a computation, it must be at the CPU, which means one question we want to ask is, how fast can we get the data to the CPU? Okay, and in Python, we don't have to handle any of that, right? So for example, we do var1 equals to 20, and we do var2 equals to 36. When we do var1 plus var2, it's not like we go and think about where these variables are stored inside the memory. We don't really care about that because Python abstracts us away from these details, right? So that is the good thing about programming. It is handled. These nitty-gritty details are handled by the operating system, and you don't have to care about any of those things. But it's still good to understand the structure of these, the general outline of where and how memory moves. The second is, can we, the CPU also gives us ability to vectorize operations. So what does it mean to vectorize operations? It means that, for example, if x1, if y1, x2, y2, x3, y3, the CPU has the ability to compute all of this in just one instruction, right? So we don't have to do this sequentially. We don't have to compute this first, second, and third. We can actually just do the whole thing in one go. But there is a catch, which means that we need to do, in order for it to happen at one go, they all need to be in the CPU because, as you said, all the math happens inside the CPU. So for us to vectorize this operation, for us to vectorize these three operations in one go, they need to be inside the CPU. So that's one point. I hope that makes sense. Now, then we need to think about what are the memory access patterns, right? If you can think about a block of memory. So for example, this is a memory block, right? And you can think of it as sort of like a box, and then, let's say this is 1 byte, 1 byte, 1 byte, and so on and so forth. Now, the thing about the data transfer is that if you want the data, if you want to access let's say 5 contiguous blocks of memory, and we want to transfer them at the same time, we can do so, right? So this can basically, the bus frequency determines the number of cycles of data transfer. And if they are all together inside physically on the memory, then we can transfer them in one cycle. So we can transfer in one cycle. On the other hand, if there's, sort of scattered about somewhere in memory. So for example, here, these are just random blocks, and then we want this, and we want to access these 3 different data points inside the memory. Then we require 3 different transfers. Okay, so if you want to ask the question of how much data can we exactly transfer in one cycle, then that is answered by the bus width. So of course, the wider or the number of wires are a lot, then you can transfer more data in a single cycle. How fast the cycle is determined by the bus frequency, and whether we can vectorize the operate and whether we can transfer contiguous blocks of memory depends on how they are laid out inside the memory, and whether we can vectorize the operations is determined by whether we can get them to the CPU at the same time, which basically means that we need, if the data points that we need are inside physical memory side by side, that means we can transfer them at the same time, which means they will be in the cache at the same time, which means that we can do the vectorized instructions inside the CPU. And these vectorized instructions are called single instruction, multiple, I can't remember what the acronym was, but it's called a SIMD instruction, right? Now, okay, so this is about a general computer architecture. So let's move on, right? So I hope that makes sense. Did I miss anything? Okay, if you want to know things like clock speed, usually this is measured in terms of hertz, and I'm sure you have seen these things around. Right? Okay, I don't think I missed anything else. So let's move on. So now let's go on from the general computer architecture to having Python specific discussion. So if you're in a language like C++ or C, then you're gonna have, how are you going to store a int array, right? So inside an int array, what is happening is you store all of the data, because we already know, right? Inside an int array, we already know the data type is going to be all integers, and all the integers take up, let's say int 64, then they're all 64 bits, and we know exactly how much space that it is going to take up, right? And inside this int array, we can't have things like a number, and then we can suddenly have some string inside this array, because then it is not consistent. Like, it is a static array with a homogeneous data type. But inside Python, all right, we can have we can have anything really. So for example, here we can have a list, and here we can have one data frame. We can have a pandas data frame, and then we can do this. We can have 6, and then we can have null, and basically we say that the data type is heterogeneous. And Python does this by what is known as a dynamic array and reference pointing. So the content inside a Python array is not actually this data frame, right? It's actually a memory address. So for example, it's like I don't know, 011, and this points to another place in memory where the data frame resides in, right? So inside C, if you go to the place in memory, we know, okay, this is actually, the list itself has these data types, has this homogeneous data types side by side. But inside Python, inside the list, if you look inside the list, then these are all memory addresses. So this is address 2, this is address 3. So we need to go to address 3, we need to read this entry, and then we need to ask, okay, what is inside address 3? Then we go to another place inside memory, and then the actual object will be stored in that address. Which basically, if you go back to the previous discussion, means that we cannot factorize operations because they are not side by side, which means if they're not side by side, then we cannot transfer them in a single memory transfer from the RAM to CPU or from the disk to the RAM, which means that the data would not be inside the CPU cache registers at the same time, which means that we cannot factorize the operations, which means that we need to do these operations sequentially, which means that we are basically doing things a lot slower. So, okay, that was vectorization is made very difficult in Python. But of course, we can work on this problem. There are solutions to overcome this, and this is by using what is known as NumPy. So if we use things like NumPy, or we use the Python array module, then we're explicitly stating that we want, because NumPys, they will contain a homogeneous data type. So we are forcing, or we're telling Python explicitly that we are storing the same data type, and therefore, we don't need the dynamic nature of the Python lists, and therefore we do not encounter this problem, which means that we now have access to vectorization. So that is the idea. Okay. I hope this was not confusing. Okay, and I'll just add one more point, right? That you can, I'll just make a great recommendation. Okay, so if you want to understand how, if you want to understand more about these concepts that we just explained, then I advise that you purchase this book and you consume the content inside, because these are, you can go really very much into detail about these concepts, about architecture of computers and the operating systems, and how they interact, and how data is transferred within the computing blocks. But I'm not an expert on that, and I know, like, to be honest, I'm probably a decent programmer, but at best I'm an okay programmer, and I'm definitely a worse teacher than I am a programmer. So for sure, some of these concepts can be brought across in a lot clearer fashion. So I do recommend you to read these books and explain these concepts in beautiful detail, and it will be very enlightening for you. Okay, so for us, we're just implementing it, and you can follow along. But if you want to understand the reasoning behind why we're doing some things, you're going to have to check these books to get a clear idea of why we're doing what we're doing. Okay, so let's go back to our code.